I want to show you a few slides to the frost risk. The frost can, in plaster or in masonry, can damage the structures. We have seen pictures of that yesterday. That will happen if the pore filling degree is smaller than 0. So it's bigger than 90%. Because the water, if it freezes, it will increase its volume about 10%. The problem is if you don't know when is the pore filled bigger than when the pores are filled, or you don't know if the pores are filled more than 90%, because small pores can be filled faster than bigger pores. So it's always a mixture in the different pore sizes, and so maybe the pore filling degree depends on the pore size and can be the critical saturation, which can be reached, is lower than 90%. That's the picture again I showed you yesterday with some calculations and measurements for that, and you can see this is the measured profile. Yeah. No.
The top one is the measurement and the bottom one is the calculation.
Yeah, right. These are the measurements, and you can see the highest water moisture maximum is over here between 3 to 6 centimeters, something like that, and that's the reason why it can spell off whole pieces of the brick. That's a calcium silicate masonry. You can see this dots. We have shown that yesterday, and for that we know that the critical water content is for frost is at 12% per mass. Somebody measured that with tests, and the calculations show that over here that's the temperature outdoor, so that's 0, that's the rain, and you can see if there's no coating on it, you get like with the rain, you get this peaks, water is sucking in and it's drying out again, and you get only short times with values higher than 12 mass percent. And if there's no frost at this time, you probably won't get any problems or any frost damage, because the brick can dry out. If you coat it, that's the upper line, you can see as it's cold outside, the moisture is close behind, or is behind the coating. So the water content is higher, and during the rain events, there's only a little bit water which can come or can be sucked into the brick, because it's coated. There are only some imperfections, and so there's no high influence. But if there's getting some water in there, it cannot dry out, because the coating is quite tight, and so you have some longer times with values higher than 12 mass percent, and you will get this little spalling effect around the holes. We also saw this yesterday, but not with this graphic. That's quite interesting. That's the water content in volume percent, doesn't matter, but with and without interior insulation. And you can see with interior insulation, the water content is always higher in the wall. We talked about that yesterday as well. For the corrosion, that's a double layer, or that's a, how do you call it? That's a reinforced fake facing with an EPS insulation, and there are this reinforcement bars in it, and they can start corrode after the carbonization of the concrete is stopped. Yeah, after the concrete is carbonated, the corrosion can start. You know, the concrete usually builds like a basic, or like a, it's like, the concrete can, the steel in the concrete usually cannot corrode, as the concrete is a
alkaline.
Sorry?
An alkaline.
Yeah, it's in German it's called basisch, basically. It's an alkaline milieu, and then when CO2 is coming into the concrete, it will carbonate, so the alkaline will stop and
becomes acidic.
It can corrode. Okay, we did some simulations for that, and we have seen that the moisture in this outer facing, this concrete facing, is quite high. We get relative humidities up to 95%, and if you analyze this with this, or if you use, there's Marquardt, I think he's in the United States now, but he was at Berlin at this time when he wrote that. He did tests, and after the carbonization of the concrete, he saw that there's no corrosion if you have humidities lower than 80%, and so the corrosion starts with humidities higher than 80%, and so there's we had an idea how to retrofit. We just put another insulation in front of the facing, and then we did calculation with two different materials. One is mineral wool, one is EPS, and you can see if you use an EPS, that's the dotted line, it needs about 2 years, something like that, to dry out, because the moisture from here cannot go out because it's quite diffusion time. If you use mineral wool, it is drying out below this 80% after half a year. So in this case, mineral wool should be, or is much more suitable. These are the field tests by Marquardt, and you can see that's a mineral wool insulation. That's behind the insulation, and that's behind the cladding, or behind the, I think it was closed with this concrete wall or something like that. And you can see on the one side of the insulation there's corrosion, on the other side there's no corrosion. That's just because the moisture is going to the cold side of the insulation. Yeah, microbial growth. I showed